So the first talk is Alejandro Becerra, a postdoc in my lab, and I just give you a little idea who he is. He came from Luis's lab, and when he came around looking for a position, I asked for a recommendation, and Luis gave me a very short recommendation. I said, "What can you tell me about this guy?" And he goes, "Take him." And, it was one of the best decisions I made, and that's I try to compare other recommendations I get to that. And given the results that he'll talk about today, he tends to be a little to lowball things. He's basically achieved something that people have been trying to do for quite a long time and done it unequivocally and leaving the previous results in the dust. And that title, I forced them to use that title as opposed to this much more milder. And so bear in mind, because that's really the achievement here in that title.
Thank you very much for the introduction. Well, today I want to talk about the work that we have been doing at NIST in the group of Alan Migdal. And this work has been done in collaboration with people at LTS, Laboratory for Telecommunication Sciences, Jerry and Jan, and Julius Goldar, a professor here at the University of Maryland. We want to study how we can take advantage of the resources that quantum mechanics can provide in order to perform better measurements. In particular, we are interested in the discrimination of multiple non-orthogonal states beyond what's considered the classical limits. The measurement of state of a quantum system with intrinsic noise is a fundamental problem in quantum mechanics. This noise limits how well we can measure this state of such a system. On the other hand, measurements that take advantage of the quantum properties of these systems can perform tasks that are beyond the capabilities of conventional measurements. And using these measurements can enable many quantum information tasks. For example, generate secure communication using quantum key distribution for the preparation of quantum states of light and matter using heralding. And in particular, the particular interest for us is to increase the sensitivity of different measurements. Among these enhanced quantum measurements, we can find the field of quantum metrology, where the task is to perform parameter estimation beyond the classical limits, where this parameter has a continuous spectrum. An example is, for example, trying to measure the phase shift in interferometry beyond the classical limit that is, corresponds to the short noise limit or standard quantum limit for this kind of measurements. What we are interested in is a discrimination of non-orthogonal states. The non-orthogonality of these states made the task of discriminating among them with total certainty impossible. Therefore, the task of the state discrimination is trying to measure these states to distinguish among these non-orthogonal states beyond the conventional limits, that is called the standard quantum limit. The theoretical predictions have been around for more than 30 years, and no demonstration had been observed until very recently for the discrimination of two coherent states below the standard quantum limit. And it was with margin. It was 0.2, only 0.2 below the standard quantum limit. Our interest is studying the discrimination of multiple non-orthogonal states, in particular coherent states in MRE phase shift keying format. We know the strength of the field, and we are trying to figure out the phase of these coherent states. This is a little bit, the discrimination of multiple states is much harder task. In particular, we want to, today I'll talk about our efforts in the minimum error discrimination, where we have been working with a strategy that can, in principle, allow for discrimination of multiple non-orthogonal coherent states below the standard quantum limit. And I'll describe our implementation of a receiver for the discrimination of 4 non-orthogonal states that can reach beyond a level beyond the standard quantum limit. Besides a fundamental interest of this work, since coherent states coherent states of light can travel over long distances, allow for multi-level encoding, and are resilient to losses. This receiver can be applied to quantum communications, such as quantum key distribution, and in principle can allow for communications below the standard quantum limit, where amplification is not allowed, such as in free space, and can increase the information that can be transmitted on the communication channel. Coherent states are characterized by two parameters: alpha, that is the amplitude, and phi, that is the phase. In the phase state, the amplitude is given by the distance from the origin to the state, and the phase is represented by the angle. Of particular interest in communication is Emery phase shift keying is a multi-element alphabet communication scheme that uses multiple coherent states to encode the information in their phases, in the phase of these coherent states. And this phase is given by this equation, and the set of the states in the Emery phase shift keying format look like this, with the same intensity but different phase. Two very simple examples is when m is equal to 2, that is binary phase shift keying, and m equals 4, quadrature phase shift keying. For binary phase shift keying, the state can take, the signal can take two states, alpha and minus alpha, and we can encode 1 bit of information in this signal. On the other hand, for quadrature phase shift keying, we can have 4 available states, alpha minus alpha, I alpha minus I alpha, and we can encode now 2 bits of information in this field. It is attractive for communication because for higher modulation formats, we can increase the information that we can encode in these coherent states. However, these states are non-orthogonal. These states have this noise around there, and this noise produces some intrinsic overlap among them and makes the task of discriminating among them with total certainty impossible. It will not allow for sometimes having inclusive results. Therefore, any kind of deterministic measurement or device trying to discriminate among these states will produce unavoidable errors. The minimum error of the discrimination of these non-orthogonal states by direct phase-sensitive detection is given by the standard quantum limit. And this standard quantum limit is the minimum error that can be achieved by conventional technologies or conventional measurements based on direct detection. For example, one of the examples is for the discrimination of two states, the standard quantum limit is given by the homodyne limit. And for states, quadrature phase shift keying, the standard quantum limit is given by the heterodyne limit. And this heterodyne limit measures simultaneously the two quadratures of the field. And this heterodyne measurement gives the standard quantum limit for higher numbers of input states. However, this standard quantum limit is not the ultimate limit allowed by quantum mechanics. The real quantum limit is given by the Hellstrom bound. This Hellstrom bound is the achievable if we want to use any kind of quantum resource that we want to measure these particular states. This plot shows an example for the discrimination of 4 non-orthogonal states in what's called quadrature phase shifting format. The error probability as a function of mean photon number for the standard quantum limit at the Hellstrom bound. We observe that this Hellstrom bound is much lower than this standard quantum limit. And this huge gap has motivated extensive research on finding and implementing optimized discrimination strategies that can discriminate in general among multiple non-orthogonal states with error probabilities below the standard quantum limit and possibly approaching the Hellstrom bound. This is what we are interested in. We have been working on a strategy, discrimination strategy, that can, in principle, discriminate multiple non-orthogonal states below the standard quantum limit and approach the Hellstrom bound. This strategy is based on displacement operations, adaptive measurements, and single photon counting. In this strategy, the input field, alpha, enters the measurement apparatus that we'll call the receiver in one of the possible states of the Emery phase shifting format, with a given and known amplitude but different phases. And the receiver implements n adaptive measurements in a feedback way. And in each adaptive measurements, the receiver acquires some information about the input state and uses this information to optimize subsequent adaptive measurements. More specifically, so this is supposed to be a bin splitter. where we perform the displacement operation. In each adaptive measurement, the receiver tests a possible hypothesis of the input signal, beta, and uses a local oscillator to perform a displacement of the input state alpha to alpha minus beta, and detects the photons in this displaced state. If, for example, the hypothesis is correct, alpha is equal to beta, and this displacement results in vacuum. If this is not correct, the displacement results in a general coherent state alpha minus beta. If we look at the detection result, and we observe that this detection is different than zero, we know for sure that this couldn't come from a vacuum, and therefore the hypothesis is not correct. The information about given by the detection result and the field and the hypothesis is used to optimize this subsequent adaptive measurement. So the way that it does it, we'll focus here in the first feedback period. The receiver prepares a local oscillator to test the hypothesis beta, and displaces the state to alpha minus beta and detects the photons in this displaced state. Now the receiver uses Bayes' rule to calculate the updated probabilities for all the possible input states that depend on the previous probabilities that for feedback period 1 correspond to the initial probabilities and depend on the detection probabilities that are given by the Poissonian probabilities that depend on the hypothesis and the detection result for all the possible input states.
So is each one of those a duplication of alpha n times, or are you taking one pulse that has mean number of alpha photons and splitting it up into n pieces?
Right.
Back.
Right. So coherent states, if we slice them in time, they're still coherent state and they have the same property that lower mean photon.
Reduced by.
Yes. So when it has calculated the updated probabilities for all the possible input states, it calculates the most likely state to have entered the receiver that corresponds to the one with maximum a posteriori probability, and defines the new hypothesis to be tested in the next feedback period as this most likely state. At this point, the updated probabilities of feedback period 1 become the previous probabilities of feedback period 2. And this process is repeated n times, as many times as the number of adaptive measurements in this receiver, and at the end, the most likely state to have entered the receiver, determined by these last adaptive measurements, defines the final decision of the receiver that we compare it to with the input state to calculate the probability of error. We have studied this strategy for the discrimination of different numbers of non-orthogonal states and different adaptive measurements, and we have observed that this strategy can perform a discrimination process below the standard one-to limit in these cases. This plot shows the error probability as a function of mean photon number for the discrimination of 4 non-orthogonal states in what's called the quadrature phase shift keying format. For this strategy, applying different numbers of adaptive measurements, 4, 8, 16, and 128. And we observed that this strategy can discriminate in principle below the standard one-to limit in all the cases and approach the Hellstrom bound as the number of adaptive measurements increases. We observe this behavior as well when we are discriminating more than 4 states, input states. We use this strategy to demonstrate a receiver for the discrimination of 4 non-orthogonal states in a quadrature phase shift keying format. This receiver applies 10 adaptive measurements and has high detection efficiency, 72%. And we observe that this receiver can indeed discriminate below the standard one-to limit these states. Here I am showing the diagram of the experiment. We use a 632 laser, helium neon laser, that together with an acoustic modulator prepares pulses of light of 26 microseconds at a rate of 11 kilohertz. These pulses enter into a Mach-Zehnder interferometer, where a 50 beam splitter splits the power of these pulses in two paths. The upper path is attenuated by a factor of 100. And a phase modulator PN1 prepares the input state to be discriminated, prepares the phase of the input state to be discriminated in one of the possible states of the quadrature phase shift keying format. The lower path is used to prepare the local oscillator phase reference field with this phase modulator PM2. At this point, the local oscillator is 100 times stronger than this input state. The input state and the local oscillator interfere in a 99-to-1 beam splitter or combiner, such that at the output of this beam splitter, these two fields have the same strength, and we can perform this perfect, or the interference, or the structural interference, or the displacement operation. The photons in this displaced state are detected with an APD avalanche photodiode with 84% detection efficiency at this wavelength 632. And the output of this APD is directed to an FPGA. This FPGA contains the whole strategy that I just described. Processes the APD output in real time, figures out which one is the most likely state, and uses fast feedback to adapt the phase of the local oscillator to optimize subsequent adaptive measurements. The detection efficiency of this receiver from the point where the state is prepared to the point where the state is, the field is detected, taking into account the APD detection efficiency, is 72%. And the visibility of the displacement operation is 99.7%. This experiment requires phase stability. We use a 780 laser, a second laser at 780, whose frequency, we will stabilize its frequency to using an atomic line of rubidium, the laser that Ian provided, the diode that Ian provided, to lock the interferometer. We use a diode, diachronic mirrors, that have high transmittance at 632 and high reflectance at 780 nanometers. The 780 light propagates in the opposite inside the interferometer in an opposite direction as the 632 nanometers pulses, and we detect, using a differential detector, we detect the interference from the two output ports of the 50-50 beam splitter. We use this output of this differential detector to feed back to a PCT, piezoelectric transducer in the back of a mirror, to look at the interferometer, the relative path length difference in the interferometer. The way that we run this receiver is in a 50% duty cycle. It means that 50% of the time we are locking the interferometer, and 50% of the time we release the interferometer and we send light pulses at the single photon level to perform our experiment. The FPGA controls the whole experiment, prepares the input state to be discriminated, and perform the discrimination process in real time. After the discrimination has been done, the FPGA transfers the data to a computer for further analysis. We use this receiver to discriminate 4 non-orthogonal states with mean photon numbers from 1 to 20. This sample of the experimental data, where we have prepared an input state with, that corresponds to minus I alpha, with a mean photon number of 5. This table shows for each feedback period from 1 to 10, the hypothesis histories, and the photo detection history for each feedback period. In the first feedback period, the hypothesis is always 0. We define it as 0. And in this feedback period, we detect a single photon, well, a photon here, and the receiver figures out what's the most likely state to happen to the receiver based on this information, and this new hypothesis in the subsequent feedback period. That is the one with phase pi. This process is repeated 10 times, and at the end, the most likely state is the one with phase 3 pi over 2, that corresponds to the final decision of the receiver. And in this case, coincides with the input state and corresponds to a successful discrimination.
So typically, what are the probabilities of all 4 states?
Depending on the input state is always 1 over 4. So
but you said the most probable one is the answer it gave. What is the probability of all 4? Because you have those probabilities too.
It depends on. Sorry. It depends on how. Depends on the measurement. So these probabilities are changing over time. So as we increase, as we perform each measurement, our confidence on the measurement starts to build up.
But say for this particular example, at the end, do you have any idea what the probability was that it was really pi over 2 or pi over 0 or some of the other ones that were?
Around 80 something, the probability. It was 80 something percent.
That it was the one that you
right, if I recall correctly.
Okay.
Yes. For this particular case.
Should have said that in
This plot shows our experimental observation for the discrimination of 4 non-orthogonal states in a quadrature phase shift keying format performed by this receiver as a function of mean photon number from 1 to 20. The blue dots with the error bars correspond to the experimental observations, and the X bars are the theoretical simulations. We observed that this receiver can discriminate these 4 non-orthogonal states with error rates below the standard quantum limit for a range from 2 to 15 mean photon numbers, and can reach error rates as low as 6 dBs below the ideal perfect standard quantum limit, and up to 13 dBs below the standard quantum limit under the identical conditions of detection efficiency, 72%.
What was the previous high water mark?
0.2 dBs.
0.2, okay.
And it was done only in 2 states. It was performed only in 2 states, and it's a way easier problem. The blue is the theoretical prediction for the same additive measurements if we had perfect detection efficiency and perfect visibility. The reduction in detection efficiency makes this a straight line approach to the standard quantum limit. A reduction in visibility produces this curvature. The visibility is more important. The reduction in visibility is more important for high mean photon numbers because a reduction in visibility produces leakage. We are not perfectly displacing to vacuum the field. And there is some leakage that leaks and is detected by the APD. And this leakage increases for high mean photon numbers. Okay, with this, I want to conclude. I described the implementation of a receiver for the discrimination of 4 non-orthogonal states below the standard quantum limit. This receiver can discriminate these states below the standard quantum limit for a wide range of input powers and can reach error rates as low as 6 dBs below the ideal standard quantum limit. And also can be scaled to discriminate higher numbers of non-orthogonal states. That's it. Thank you very much.
Well, I have been asked to introduce the next speaker, I think because he collaborates with me. Alejandro Lobos, this is his 2nd year. He was hired as a JQI fellow last fall. And, I mean, not the last fall, the fall before, right? Alejandro, this is. And Alejandro is originally from Argentina. He went to this very famous Theory Institute in Bariloche, very up, beautiful place. And after getting his PhD there in theoretical physics, he did a postdoc in Geneva with Thierry Gamachi. And Alejandro is a world authority on one-dimensional system, bosonization, dimensional group technique, and so on. And he has been working on a number of problems at Maryland, and I do not really even know about all of them. But the one that I'm familiar with is trying to understand the interplay of interaction and disorder in these new topological superconducting wires that are quite big in JQI. These are the wires where putative Majorana modes might have been seen by various experimental groups. And since there's a P-wave superconductor, and P-wave superconductor is a spinless superconductor which is not immune to disorder like ordinary superconductors are, it's very important to understand the effect of disorder. And in one dimension, it's very important to understand the effect of interaction. And Alejandro has been using very powerful theoretical techniques to understand that. And I'm hoping that's what he's going to talk about. I don't really know what he's talking about, but I hope that's what he'll talk about.
Okay, thank you very much, Shankar, and I want to thank the organizers for inviting me to present our results. So yes, as Shankar was saying, I'm going to talk about the interplay between disorder and interaction in one-dimensional topological superconductor. This is a work done in collaboration with Roman Lucin, present at Station Q in Santa Barbara, and Professor Becerra. And let me start this talk by presenting this sort of chronological introduction that you might have heard many, many times by now. But basically, in 1937, Ettore Majorana introduced the idea that the Dirac equation could admit real solutions in addition to these complex solutions that Dirac derived by himself. And these real solutions physically represent particles which are their own antiparticles. And this notion opened a very exciting field in higher energy physics, particularly related to neutrino physics. But for our purposes, we want to focus this discussion in the consequences of these to solid-state systems. So in that respect, it was proposed around 15 years ago that in P-wave superconductors, some of this physics could also be observed. And that's very interesting. And the way to understand this idea is actually very simple. As you know, the excitations above the superconducting ground state are the so-called Bogoliubov excitations. And these excitations are actually a linear combination of electron and hole wave functions. And the particularity of P-wave superconductors is that in certain circumstances, for instance at the defects or for instance in the interior of a vortex, these superconductors admit solutions at zero energy. And the idea is that at zero energy, there is a very particular relation between these U and V parameters that compose this wave function. And they are equal, and therefore, is it very easy to understand that in this condition, this Bogoliubov excitation satisfies the defining property of a Majorana fermion. So that's very exciting, and that opened a very interesting field also in solid-state physics, because of the possibility, because these quasi-particles in these superconductors have non-abelian statistics, and that enables to use these objects to perform topological quantum computation. However, the problem that we have in solid state is that P-wave superconductors are not that common. And that's a very important problem. And in that respect, people have been thinking of different ways to engineer these P-wave superconductors out of, for instance, at the interfaces of S-wave superconductors and topological insulators, or at the interface between a superconductor and the strongly spin orbit coupled semiconductor, like in these two cases. And there are many more examples that I don't have the time to explain here. But let me go to something much more basic. And I would like to, I mean, if you want to understand how a Majorana state appears in condensed matter physics, condensed matter setup, probably the most easy way to understand it is with the JQI chain model. This is actually a toy model that describes spinless electrons in a 1D discrete lattice. And in this Hamiltonian, we have a hopping term here, a P-wave pairing interaction that couples electrons which are nearest neighbors, and some chemical potential term. And the idea is that one can change the basis. It's just a rotation in the electronic states of this problem. And one can define these A operator and B operators, which by themselves, these are Majorana operators, as you can easily check. And if you try to express this Hamiltonian in this basis, you obtain this new picture here, where the green row of dots represents a chain of A Majorana operators, and this other row are the B Majorana chain. And actually, these operators are coupled via these interactions here. This is nothing but re-expressing this Hamiltonian in this new basis. And what Kitaev realized is that in this system there are two phases actually. One is a sort of trivial phase in which the vertical ranks dominate. And if these vertical ranks dominate, actually you can very easily understand that this composite object is actually the original blue dot, which is the original fermion. So nothing interesting happened. However, there is another phase, which is much more interesting, in which the diagonal ranks dominate. And in this case, you can very easily see that there are two uncoupled Majorana operators that are left at the ends of the wire. So actually, in the finite length chain, the story is not. This is not the whole story. What happens is that these, in principle, degenerate states, which are localized at the ends of the wire. So the wave functions that describe those states actually have some spatial extension, and they can overlap to some extent in the bulk of this 1D wire. And because of this overlap, there is some interaction between these two modes. And this original degeneracy is lifted. And these new states, which are bonding and anti-bonding combinations of these two Majorana states, are actually exponentially split with the size of the system. This psi here is the localization length of the Majorana bound state, which is inversely proportional to this parameter delta. This would be our defining property for a topological 1D superconductor. The fact that these states are exponentially split. So this system has exponentially split states around zero energy. So this is a very nice and neat example, but real systems are much more complicated, right? So one can ask how the different existing interactions in a real system can modify this picture. And one easy question is, for instance, what is the effect of disorder in this Kita chain, or what is the effect of interactions? And those, let me tell you, are not new questions. People have asked those questions a long time ago, but the particularity is that because the system is very complicated, either the effect of disorder alone or interactions alone have been addressed. And I don't have time to dwell into many details, but the idea is that when disorder is introduced in these wires, there are a bunch of subgap states that appear. And the subgap region becomes to start populated with low energy states. And the density of states acquire some sort of divergence near zero energy. So that even more, if disorder becomes too strong, such that this mean free path is smaller than 1/2 of the localization length, actually the system experiences a topological phase transition towards a non-topological phase. So that's very bad for any topological quantum computation, for instance. And also, even in the topological phase, when the system is still topological, the splitting of these Majorana bound states is modified by this fact. So it increases from the clean limit. And this also has some impact, and it's important to characterize these effects for topological quantum computation. On the other hand, the fact that so people have also realized that repulsive interactions can renormalize the effective p-wave pairing to lower values. And this is also bad because delta is the size of the gap in this superconductor, and this is what provides topological protection. So we want delta to be as large as possible. So from our perspective, so one can ask the following question: what is the effect of the simultaneous presence of these two things on a same wire? And clearly this is a theoretically motivated question. We want to understand what are the details. So we know that these two effects are detrimental, but how are they detrimental? How this affect the topological stability? But moreover, this is not only theoretical, because nowadays we have systems which have been studied, experimental systems, where all these interactions, all disorder interactions come together. And it is very hard to disentangle these effects in a one-dimensional geometry. So to study this problem, we studied this model, which is here divided in 3 pieces. So this is a model of which is expressed in the continuum, and it incorporates the presence of a one-dimensional spinless superconductor, a disorder term, and an interacting term. So this first term here is nothing but the Kita chain, but in a continuum version. So here we have the kinetic energy term and the chemical potential, and this is the p-wave pairing term that gives rise to the topological superconductor ground state. In addition, we have introduced this disorder potential, which we assume to be Gaussian distributed with zero average and this delta correlated second moment. And finally, we introduced this short-range repulsive interaction between electrons. And the kind of idea, the kind of method that we're going to use to solve this problem is the so-called abelian bosonization method. I don't want to enter into technical details, but let me tell you that this is, so the main idea of this method is that in one dimension, all the excitations become collective. That means that one cannot define a single, for instance, single particle excitations. This is intuitively, can be intuitively seen, because if you want to move one electron in a one-dimensional chain, actually you have to move all the other electrons. And this results in the collective motion of the electronic fluid. Something that you can probably also experience in a very, in this common situation in the highway, for instance, when you are stuck in the traffic. But more seriously, this idea can be used to define two fields that describe the motion of the electrons in this one-dimensional geometry. So this feature allows us to define a field that we call phi, that this, in terms of which the electronic density can be expressed. So that's some technical issue that I don't want to explain too much. But basically, the density will depend on this field. That's what we need to retain here. And the other field that we need to describe the quantum mechanical nature of this problem is so-called, is a dual field canonically conjugated to this phi, which we call theta. And physically, this field, theta, is related to the superconducting order parameter via this relation. So these two fields together are enough to describe the whole the physical features of this problem. And if you want to understand more physically what is this commutation relation, this is nothing but the phase and density commutation relation that you can find, or phase and number commutation relation that you find in any superconductor. So that's the more physically motivated case. So the great advantage of this bosonization method, is that it allows us to introduce to consider interactions exactly. So this term, which is very hard to take into account in the fermionic language, in the bosonic language is very easy to handle. But the price you pay to use this method is that these two interactions here, disorder and superconductivity, are very hard to describe. So our strategy would be to consider this Hamiltonian together with this piece and use perturbation theory to introduce these two terms and see what happens and what kind of information we can obtain out of that. So let me jump to the main results. So we use the so-called perturbative renormalization group framework to extract some properties of this system. The idea of this method is the following. It's very simple. Our Hamiltonian actually is in the continuum, and in order to have a well-defined Hamiltonian, we need to consider a high energy cutoff. So our theory is only valid up to a certain energy cutoff. We cannot ask questions beyond that limit. And now we ask the following question: what happens with the parameters of this Hamiltonian, namely delta dB, which is the strength of disorder, for instance, when we rescale a little bit this high energy cutoff? How these parameters flow? Do they increase or do they decrease? And this feature gives us a very useful information of the system, because it tells us if these interactions tend to, which phases are being stabilized by the presence of either these or these interactions. So, so we have derived three main RG flow equations that describe superconductivity in the system, disorder, and this parameter K, which is a feature of this model. Basically, this dimensionless parameter K encodes the strength of interactions. This is the nice feature of bosonization. So in this bosonized language, K equal to 1 means non-interacting electrons, whereas K smaller than 1 are repulsive, or for K bigger than 1 are attractive interactions. So, so this is a complicated set of nonlinear differential equations. So they can be solved numerically, but in order to have an idea of what do they mean physically, we can sort of eliminate for the moment this equation and consider that k, this parameter that quantifies the interactions, is a constant. And then the problem becomes very simple. One can very easily integrate these RG flow equations. And for instance, this one tells us that for interactions such that k is bigger than 1/2, superconductivity will become bigger and bigger as the energy of as we look at lower and lower energies in this system. This is because this prefactor becomes positive. So this kind of perturbation that grows and grows as the energy becomes smaller is a so-called relevant perturbation. And you can very easily check that if k is smaller than 1/2, this becomes smaller and smaller. So in that sense, interactions are very important to determine the fate of this superconducting pairing term. And I don't have much time to dwell into these details, but the kind of ground state that this, of course, this term favors is a topological superconductor. So the topology is basically encoded in the fact that this superconductor has two degenerate ground states, which is reminiscent to the fact that a Kitaev chain has two Majorana end states which are very near, well, for the infinite length chain are degenerate at zero energy. Another term we need to consider is the disorder. And this RG equation is telling us that for interactions such that k is smaller than 3/2, disorder becomes a relevant perturbation. That means that the kind of ground state that this disorder tends to favor is a pin charge density wave. This is a result that has been derived in the late 80s by Jamarchi and Schultz. It's a very important result given in the context of localization induced by disorder and interactions. And physically what this means is that at low energies, this disorder tends to distort the density field such that one can accommodate these strong impurities, and therefore the system becomes an insulator, actually. And the third equation that for our purposes is very important is this last equation. And this is an interesting equation because here a lot of action happens, even if it's not very obvious. But basically, one can already intuitively understand that there is a competition between the superconducting ground state and the insulating ground state. And this competition occurs in our method in this equation. Mathematically, this can be seen because k, which is the parameter that quantifies interactions, grows because of this superconducting term, but tends to diminish because of disorder. So these two opposing effects is a consequence that that these two interactions fight each other for the ground state. And so what we did was to solve numerically these RG flow equations for a particular body of interactions. This means very strongly interacting repulsive interactions. And in this plot, what I'm showing is the strength of disorder in this axis and the strength of superconductivity in this axis. So in this plot, one can notice three things at least. First of all, for this initial value of interactions, you can see that if you initially start from, let's say, this initial condition, both disorder and interaction and superconductivity tend to increase. That means that this, so the system is actually fighting, so these two interactions are fighting for the ground state. Both of them wants to take over the ground state. And the second thing we can notice is that eventually in this regime, which means strongly coupled superconductor or strongly disordered system, these lines tend to diverge. And that's a consequence of the fact that these two ground states are not compatible. So the system has to decide whether to become a superconductor or an insulator. So something that can be seen in this language is the existence of a critical line which is very interesting to analyze. I don't have time to explain here, but basically this critical line is a line of quantum phase transitions that separate these two ground states. And the third thing you can notice is that even in the presence of disorder and interactions, which are detrimental terms to this topological superconductor, if you correctly choose your initial conditions, you can end up in this topological superconductor. And that's very important for applications. And as a final result, one can calculate what is the splitting of these Majorana bound states, both in the presence of disorder and interactions. So we were able to reproduce, first of all, the results that I mentioned in the introduction. Which is encoded in this term if you eliminate this part. But if you allow for interactions, this term appears. And this term encodes, so this term, of course, depends on K, which is the parameter quantifying interactions. And so we have been able to extend the results of Brower and collaborators to this very non-trivial case. And actually, this slide summarizes all the most important results we have obtained. So I leave you with this last slide, and I want to thank you for your attention.
Okay, a quick introduction for the last postdoc speaker. This is Phil Richerme, and Phil comes to us. He's a postdoc in my group, coming from Jerry Gabriel's group at Harvard, where he earned his PhD, spending most of his time at CERN on the anti-hydrogen project, where they were the first to observe several trapped anti-hydrogen particles. And I first met Phil actually probably about 6 or 7 years ago from now, before now, when I was in Michigan trying to recruit him as a graduate student there at Michigan. But maybe it's better that I see him now, because now he's MIT educated as an undergraduate and Harvard educated, and the natural progression is he should do a postdoc in Maryland. So, thank you, Phil.
Thank you very much, Chris, and thank you all for staying all the way to the end of this postdoc marathon. I'd like to share with you some of the recent work that we've been doing in the Monroe Group, where we've been simulating quantum many-body physics using linear chains of trapped ions. The basic idea here is that if you have some complicated many-body system whose behavior you wish to calculate, you can map that system onto another system over which you have good control, and then investigate the physics that you're interested in using this well-controlled quantum system. Now, it might seem like kind of an obvious statement in the title that you need many trapped ions in order to simulate a many-body quantum system, but in fact, there's a profound feature here between this one-to-one correspondence in quantum simulation. For instance, if you have some 30-spin many-body system, it only takes 30 ions to simulate that. Now, compared to classical computation, there's an exponential scaling there that's required, so you'd need 2 to the 30 numbers just to describe the wave function. That takes about 8 gigabytes of RAM. If you then want to build a 2 to the 30 by 2 to the 30 matrix so that you can evolve the Schrodinger equation with that wave function, you're likely to end up with a result that looks something like this, rather than the result that you're after. So this is a primary motivation for why we want to do quantum simulation of trapped ions. And for this reason, our group has been pursuing this sort of work for several years. Early work has looked at mapping out the ground state phase diagrams of Ising-like spin Hamiltonians, observing the onsets of quantum phase transitions as we increased the number of spins from 2 ions to 9 ions, and then probed some early studies of frustration with about 3 spins in the system. In this talk, I'll focus on some of the recent results that we've had. In both cases, we start with an anti-ferromagnetic Ising model. And in the first case, we vary the range of our long-range spin-spin interactions, and that actually gives us enough to tune the amount of frustration that we have in our system. Second, we start with that same anti-ferromagnetic Ising model, and then we add a longitudinal magnetic field. And what this allows us to do is to create and observe new spin phases that we couldn't otherwise access. And finally, in the end, I'll talk a little bit about some of the current pursuits in our lab, where all of these sorts of investigations are centering around studies of excited states and dynamics in our systems. All of the experiments that we do take place inside of an RF Paul trap. It's housed in this vacuum chamber here. Into the Paul trap, we load ions that are ytterbium-171 as the species. We adjust the trap voltages so that all of the ions lie along a linear chain. If we zoom in on any one of these ions, way down towards the ground state, we have this hyperfine splitting. These two states serve as our effective one-half system. So we label the F equals 0, MF equals 0 as the down state, and the F equals 1 here as the up state. These two hyperfine levels are split by about 12.5 gigahertz, 12.6 gigahertz, and they're relatively insensitive to external magnetic fields, which means we have excellent qubit coherence times of greater than about a second without any other magnetic shielding in the system. When it comes time to read out exactly what spin state the ions are in, we address the ions with 370 nanometer laser light. If the ions are in the up state, then this light is resonant with this S to P transition. The ion will scatter many photons, which we can then collect on an intensified CCD camera and make images of the ions like this. However, if the ions are in the down state, then that 370 nanometer light is far off resonant from any of these transitions, and we receive essentially no scattered photons from the ions. Now, in order to simulate many-body physics, we need to engineer spin-spin couplings to have the ions all talk to one another. We do this by first starting with loading our linear chain of ions into our trap, and then globally addressing the ions with two perpendicularly intersecting beams, one beam at frequency omega, and the other at omega plus the hyperfine splitting frequency, plus or minus an additional detuning, which I'll call mu. Now, in the case where mu equals 0, this is no different than just a Raman process, where we can move population from spin down to spin up by coupling through this third excited state up here. And the frequency beat note difference between these two colors is just the hyperfine frequency. It's often called a carrier transition. Now, we need to remember that all of these ions live in a harmonic type trap, which means that there are very closely spaced normal modes, both in the axial and the transverse directions, nearby to this carrier. And so what we can actually do to generate our spin-spin couplings is to now introduce these two frequency components on this beam, plus or minus mu. And if we put them tuned nearby to these transverse modes, we can off-resonantly couple to all of these modes, and it's been long been shown that such a coupling will generate an effective spin-spin interaction whose coupling strengths are parameterized by this number J. That depends on the Rabi frequency of each ion, the relative detuning relative to the transverse mode frequencies, and in general, these Ising-like couplings fall off with a power law in distance between the ions. One additional thing we can do in this system is to add a transverse field. It's transverse because this is a sigma Y term next to the B, so that's perpendicular to the spin-spin coupling direction. We can do this simply by applying another color frequency component to this beam. This is just at omega plus omega hyperfine, so that the beat node is just at the carrier. And if we apply this carrier in addition to the two sidebands with the appropriate phase shift, we can generate this term as well. So the experiments that we're looking to do, we start with this Hamiltonian, which we can engineer. The first step in our experiments, we always initialize the spins to point along the y direction. We do this so that when we turn on our Hamiltonian with By much, much greater than J, we will have initialized the system into the ground state. We then adiabatically turn down this By field over time, and if we really do this adiabatically, the system will remain in the ground state throughout the entire evolution. And at the end, we'll measure all of the spins along the x direction. We're setting up antiferromagnetic Hamiltonians here, and so the expected spin ordering we find is this staggered up, down, up, down, up, down ordering. So to give you a little bit of a flavor of how one of these experiments might go, under this Hamiltonian, we start with B much, much larger than J, and then here I'm plotting the correlation function between the first ion in the chain and all of the rest of the ions. So initially we're in a paramagnetic state, and so there's no correlation essentially between any of the ions in the chain. However, as we ramp down V over J just by a little bit, we see some of the order come out, but really not much yet. However, as V over J continues to get smaller and smaller at the end, we find this staggered order in the correlation function corresponding exactly to the up, down, antiparamagnetic order that we might expect. Now, I've mentioned before that the Ising couplings, parameterized by Jij, fall off roughly with a inverse power law with distance between the ions. And this parameter alpha, this power law fall off, is something that we actually can control in our experiments. So just by adjusting trap frequencies, we can make a change in the axial frequency of the ion trap in which our terbium are located, and by doing this, we can vary alpha roughly between a range of about 0.5 and 1.5. Now, one of the immediate consequences of doing this is that it allows us to have a knob to tune the amount of frustration in the system. As we move to longer and longer and longer range interactions, there are more and more and more antiferromagnetic bonds that become difficult for the entire system to satisfy, and the system is becoming more and more frustrated. And one of the ways that this plays out in the system is that if you look at the energy gaps between the ground state and the first coupled excited state. As you move to longer range interactions, the size of that energy gap gets smaller and smaller. And so this gives us an idea for what to do, how to experimentally probe this, which is that we can ramp the Hamiltonian down in the same way every time, and we can ramp it down non-adiabatically. And if we do so, then we'll be making more transitions away from the ground state when the gaps are small compared to when they're big. So one way to quantify the amount of frustration in the system is by looking at the structure function, which is the Fourier transform of the correlation functions that I told you about earlier. So for a ground state ordering that goes up, down, up, down, up, down, we would expect a peak in the structure function that corresponds to a lattice spacing of every other ion. And in fact, we see at that wave vector of a half corresponding to a lattice spacing of 2, we do see a peak in the structure function, but then that peak begins to get suppressed as we move from short-range interactions to longer and longer range interactions. So this is evidence of higher and higher amounts of frustration getting put into the system as we're moving to longer range interactions, and we're making more and more excitations away from the ground state. Now, using our intensified CCD camera, we can take pictures of all of these spin orderings that we're actually making in these experiments. And so we can very easily tell the difference between all of the spins pointing up or all of the spins pointing down. So when we go to make our antiferromagnetic states, we end up with the two possible degenerate antiferromagnetic ground states, either up, down, or down, up. When we do this experiment 2,600 times with this value of our long-range coupling parameter, we find about 440 times out of the 2,600, or 17%, we end up in the ground state. That's not 100% because we're not ramping the Hamiltonian adiabatically, but it's still a lot larger than the probability of getting any state at random. Now, since we are making excited states, we can look at what those look like on camera additionally. You'll notice that they're parameterized by having two spins that are pointing the same direction, pointing right next to each other, and that costs energy in an antiferromagnetic Hamiltonian. Since we have the camera, we can also plot the probability distribution of landing in any of the possible 2 to the 10th or 1,024 different states. So when we're initially in the paramagnetic state, we have a roughly uniform probability of being in any spin configuration. But then when we ramp down so that the final magnetic field is much, much smaller than the spin-spin couplings, we end up in a state where the two antiferromagnetic states are popping out with high probability compared to any other spin configuration in the chain. And the fact that these two states pop out with high probability, even though we're ramping non-adiabatically, is a rather general result. The ground state should always be the most prevalent state, no matter how adiabatically you do the ramp in these sorts of experiments. And in fact, we've used this to recently push the data up to 14 ions. So you can see 14 ion data here, where we're again making these staggered antiferromagnetic states. The total ground state probability is only about 3% in this data, but still it's quite easy to pick out exactly what the ground state ordering is. Okay, so far I've been telling you about experiments where we started with an antiferromagnetic Ising-Hamiltonian. We've varied the range of interactions, and we've observed increasing amount of frustration as we move to longer range interactions. Now I'd like to tell you about a different experiment where we start with the same Ising-Hamiltonian. Now we fix the range of J, and instead we add a longitudinal magnetic field, and then we vary the strength of this Bx that parameterizes how strong that longitudinal magnetic field is. And when we do that, we find that we observe n over 2, where n is the number of spins in the system, n over 2 discrete phase transitions as we increase the strength of Bx. So the experimental protocol here is very similar to what I've showed you before, except now the main difference is that we initialize the spins all to point along the total B field, that's Bx plus By, so that now when we turn on this Hamiltonian, we're again initialized into the ground state. As before, we adiabatically ramp down, and then in the end we measure the spin ordering along the x direction. So at the end of the ramp, when By equals 0, we have just these two terms left in the Hamiltonian. And for those terms, we can actually plot what all of the low-lying energy eigenvalues look like in the system as a function of Bx. So it's mostly spaghetti, but we notice that at 3 different points in our n equals 6 Hamiltonian, we cross 3 phase transitions. And if we zoom in to see exactly what the ground state ordering is at each of these segments, near Bx equals 0, we have the 2 degenerate antiferromagnetic ground states, as one might expect. But as the Bx term gets larger and larger, at some point it becomes energetically favorable for one of these spins up to point along this external magnetic field. And now we only have 2 spins right. Again, as we cross the next phase transition, we now only have one spin bright, and at large Vx field, then it becomes energetically favorable for all of these spins to be pointing down. We can plot some sort of an order parameter, like the number of ions bright as a function of the axial field, and we find that we get these steps in the staircase. Each of these step positions corresponds to the position of a phase transition. One of the very interesting things about this system is that these multitude of steps are only visible when you have long-range interactions. Okay, so if you had just a nearest neighbor Ising model, what would happen is that there's a massive degeneracy that makes all of those steps line up right on top of another. And these long-range interactions lift that degeneracy and allow you to see n/2 phase transitions in general in the system. Okay, so I showed you what the theoretical staircase should look like when we actually go in and take data. This is what we find. At low Vx, we have 3 ions bright, and at large Vx, we have 0 ions bright. But in general, in the middle, the data is quite heavily rounded compared to the staircase. However, we can use the idea from before that we can look at every point and figure out what the ground state spin ordering is just by looking at the most prevalent state. And when we do that, these black points here agree quite nicely with the theoretical prediction. We can also go in for any of these points and look exactly at what the antiferromagnetic, the 2, the 1, and the 0 bright ground states are that we're making, and exactly look at the character of those ground state spin orderings. We can repeat the experiment for 10 ions, where here we're plotting the 5, 4, 3, 2, 1, and 0 bright ground states, and a very interesting structure starts to come out of this data. Namely, if you look closely at the 4 bright ground state, for instance, you can't get to this state just by starting in a 5 bright ground state and switching one of these spins off. There's a completely new spin ordering that comes about as you cross each of these phase transitions. And in fact, this maps exactly onto an energy optimization problem, trying to put Q different charges onto n lattice sites and do so in the minimum energy way. Said maybe in condensed matter terms, this is identical to creating a Wigner crystal out of spins, which is something traditionally very difficult to do out of electrons. As the system size for this Hamiltonian approaches n equals infinity, then the staircase that you get out is actually one that's a fractal double staircase. And that arises due to the fact that every rational filling factor gets its chance to be the ground state, and there are an infinite number of rational filling factors. Okay, well in my last few minutes, I'd just like to talk about some of the current pursuits that our group has been going after, and namely they're all revolving around studying excited states in the system. Okay, so this is motivated in part because it's difficult, if not impossible, to calculate behavior of excited states in many-body systems, even for modest system sizes, but also because excited states are very interesting. So far in the talk, I've been focusing just down on this one state here, but in general, there are 2 to the n other states up here that have something to say about how a system might behave. So one of the things that right now we're pursuing is looking at spectroscopy of this many-body Hamiltonian. The general idea here is that we can stick with a transverse field, we can modulate that transverse field back and forth sinusoidally at various frequencies, and we can see resonances when one of those frequencies corresponds to an energy splitting between a ground state and an excited state. So in this data that I'm showing here, we're first preparing an antiferromagnetic ground state, and then we're changing the modulation frequency with which we're shaking the transverse field. And what we notice is that at 3 particular modulation frequencies, we're going through resonances. We're depopulating the ground state. And if you then go in and look with the camera what states the population is actually going into, for this resonance, for instance, we're going into one of 4 of these excited states here. And the thing that these 4 excited states have is that, located in blue, are that each of these is only 1 spin flip away from the ground AFM state. We can plot the probability of being in any one of these 4 states as a function of this modulation frequency, and it's almost always 0 except right at this resonance. So you can really see that we're taking population away from the ground state and we're putting into this coupled excited state. Similarly, if you look at this resonance, then it also goes into these states that are also 1 flip away from the antiferromagnetic states, except now the spin flip happens in the middle. And then similarly for the third resonance, we're also 1 spin flip away, except now it's in ion positions 2 and 5 here. Okay, so measuring what these modulation frequencies are allows us to map back onto the Hamiltonian and say exactly what these energy splittings are without having to know them a priori. One of the other things we're heavily interested in is studying what happens when you cross a phase transition not at equilibrium, And we expect that we might be able to pull out some sort of Kibble-Zurich-like defect scaling where we can actually predict the number of defects that we make as we cross a phase transition not in equilibrium, just by measuring perhaps the scaled correlation length at the end of the system, or maybe just by knowing how quickly we're ramping through that phase transition. And it might even be possible in our system to pull out some universal scaling behavior. In addition, we can perform experiments where we look at evolution of spin correlations in our system with a single defect and watch how that kind of defect tries to thermalize in our closed quantum system. In such an experiment, we would be creating a defect either by using some sort of an optical pumping beam or some other state preparation method, and then we can watch as that defect evolves through the system under the influence of our Hamiltonian. Now, saying all of this is predicated on the idea that we can scale up to a regime where classical computation can't say anything about how these sorts of systems would behave or evolve. And so right now here what I'm showing is some early 16-ion quantum simulations that we've done, both for antiferromagnetism, where you can see this staggered up, down, order coming out, and also ferromagnetism, where if we start in some phase that has no ordering along the magnetic field direction of mx, then in the end we have this bifurcation to all of the spins either pointing up or all of the spins pointing down. And similarly, we pushed this to 18 ions here, where we go from net zero spin to this bifurcation again of either all up or all down. If we want to continue pushing this up to about 30 ions or so, then it's very likely that we're going to have to cool down our entire ion trap to 4 Kelvin to vastly limit the background gas pressure and really improve the ion lifetime that we have in our trap. And we already have some ideas about how we're going to go about doing that. Okay, so just to sum up, I've talked about 2 experiments where we started with an antiferromagnetic Ising model. And first, we varied the range of interaction, and we've observed increasing frustration for longer ranges. Second, we've varied the strength of an external longitudinal field, and we've observed new phase transitions and phase spin ordering in the ground state. Currently, we're going after dynamics and excited states in the system, which is a really hot topic and interest for us. And just finally, I'd like to thank all of the graduate students with whom I work and all of the recent alumni on the project, without whom this work would not have been possible. Thank you.